If I run the same thing twice, I get different results. And that means that if I run something multiple times, maybe one of them is correct. So maybe if I run the same question 8 times or 16 times, and I have a good way to choose the best one, so I know how to validate the correct answer, I can spend more, but get more. And that's the main idea behind testing compute scaling.
Hi everybody, welcome to another YAAP episode. And I don't know what about you, I've been hearing a lot about test time compute scaling, and mainly I think in reasoning models and those kind of things, but not enough when we talk about agents. So today I have with me Or Dagan, our CPO here at AI21, to really walk me through about it and talk with all of us about what is test time compute scaling in agentic workflows. Hi Or.
Hi Yuval.
Nice to meet you here.
In this setting.
I'm so happy that you came here. Really, genuinely am. And maybe tell us a bit about yourself in a sentence or two.
Sure. I'm Or. I'm the Chief Product Officer at AI21. Come from a technical background, started as a software developer, and had a chance to do many different things throughout the 7 years that I'm here, from training models to building B2C AI products, and now leading our product organization.
And of course, being a podcast guest here.
And of course, being a podcast guest.
So really, I think I need to maybe get my head in order in those type of things because, for instance, I've been to GTC last year and Jensen talked a lot about test time compute scaling and showed a lot of reasoning models and all kind of those things. But when we talk about agents, I kind of need to fill in the gaps.
Sure. First of all, I think the concept of test time compute scaling can be applied on a lot of different methods and things. So one area where this sort of shines or people are discussing for a while is maybe at test time when we try to solve a benchmark, we can dedicate some of the resources to get better, to train, for example. So you probably know ARC benchmark and others. Some of the contenders, what they did is train a model or a system that when it gets the test, it uses some of the time and resources to train on the first items and then improve throughout the benchmark. So that's one way of using test time compute scaling, or use different ways of the resources at test time. Another thing, which is, I think, very common and we are all aware, is reasoning models. Because they have different budget levels, they can use tokens in a different way. So for the same task, you say, I want to put a medium budget or a high budget or a low budget, and the model uses more tokens, it costs more, but it gets to a better score because it thinks through the plan and it corrects itself and other methods that increase accuracy. But there are a lot more other methods, and some of them, or many of them, are based on the core fundamental, it's a problem and a benefit of what we're doing, and that we're using probabilistic models. So things are probabilistic. If I run the same thing twice, I get different results. And that means that if I run something multiple times, maybe one of them is correct. So maybe if I run the same question 8 times or 16 times, and I have a good way to choose the best one, so I know how to validate the correct answer, I can spend more, but get more. And that's the main idea behind testing compute scaling.
Yeah, which is much better than spend more and get less.
Exactly.
So essentially what you're saying, if I understand correctly, is that you're translating the concept of test time compute scaling to agents as doing multiple trials or multiple paths or something like that?
Exactly. So if we're taking what I just mentioned about a single model or a single LLM call, we can do the same over agents, right? I can have a task. And this is something that's already been done, especially in coding agents. For example, Cursor and Cloud Code are using that method of having like a swarm of agents or sub-agents trying to do or solve the same thing. And the first one that succeeds comes back, or other methods to choose or reduce at the end between the multiple paths. So the idea is similar. Yeah, we take the task, we give it to a few agents, and maybe some of them are more expensive, some of them are less expensive, but even doing the same thing over and over with the same tools can improve results as long as you know how to choose. I will say that while this concept is showing great results, and it is sometimes called best of n or other methods of just running multiple parallel trajectories and choosing the best one, it has a few limitations. I think the key limitation of how people are doing this today is that we're sort of doing black box test-time compute scaling. What do I mean? We initiate a lot of different agents, and they do the entire trajectory, and when they finish, they come back to us, and we choose out of it. But it means that we duplicate the resources on the entire task, which might be 50, 100 steps, 150 steps. So we're not optimal in how we're scaling compute, right? Because maybe solving this task has the first initial step of context building, if we're taking code agents, for example. And then I need to write some tests. And finally, I'm trying to solve the problem. Maybe the really hard part is just solving the problem, and I shouldn't duplicate the first few steps over 16 agents. I can do that with one agent. So getting to a higher resolution of where I open up a lot of width, because this is a hard problem, and where I can just satisfy with one or two because it's a simpler problem, requires higher resolution of agentic trajectories. And I think that's one of the main problems or setbacks of the current methods, and what we believe needs to be solved to really use test-time compute in enterprise use cases in long trajectories. A second problem, which is true in any case, is how do I choose, right? Because if we have 8 parallel tracks, we need a way to reduce at the end. We need a way to know what's correct. It's easier with code because you can run tests, and sometimes things are verified, though that in like real inference and real environments, you don't always know that you're correct. It gets harder on other tasks. So let's say I have a deep research agent, or I'm doing knowledge work in my organization. It's harder to get a very successful validator that knows how to, that knows if the answer is correct, because if it knows, why wouldn't it just run it from the beginning as the correct thing? Now, obviously, sometimes it's hard, it's easier to validate than to actually solve, but that's one of the problems. How do I validate? How do I reduce when I increase different trajectories? And that's a problem that the entire industry is trying to solve.
Yeah. So to sum up the 2 problems that you've mentioned, right? The first is how to do it efficiently in case I don't just duplicate everything, and how do I choose? It's funny because you said in the beginning, right? Let's say that I run 16 times and I can choose the correct one, then I'm good. Kind of casually mentioned that.
Yeah.
And obviously it's not easy. I know that we do a lot of work here on reducers, on validators. Can you maybe share a bit about that?
Sure. And not just about the work we do. So when we have a lot of different trajectories, there are a few methods that help, even the naive ones. So one of them is you can reduce duplicates. Maybe 16 agents ran, but some of them got the same answer. So you can reduce duplicates. If some of them got the same answer, you might say this is also maybe a signal that's the correct one, right?
Yeah,
so maybe you can do a majority vote.
Sounds very self-consistency or like
exactly. So you get some distribution of the possible solutions, and maybe just doing a majority vote helps. And what we see when we run tests is that yes, if you do a random sampling out of those 16, let's say, you basically should get the same result as running it once, right? It's the random sampling. But even things like majority vote and deduping help and increase, but they're still far from the optimal. And if we have an oracle, we see that there are a lot of gain to be had.
Just to make sure, when you say an oracle, you mean that...
Let's assume I know what's correct, because I'm doing this on the train set, and I'm testing my validator on the train set. So I know what's correct. I ran 16 items, and I know, for example, that with random sampling, I get 50, and but the optimal success after I ran 16 trajectories is 80. How do I close that gap? So one way is majority vote, another way is deduping. We can also add models to the party, and let a model choose, like give another model, a different model, a few models. We can do majority vote between them, show them the trajectories, and tell them which solution is the correct one. And as I mentioned earlier, in many things, also in math, but even in life, sometimes it's easier to validate rather to solve. And in this case, it helps. You can give a model the few different solutions, and they can vote. And we see that this gives a huge boost just by using a naive model as validator or reducer.
This is essentially LLM as a judge, right? It's
Exactly.
Not
That's LLM as a judge.
Just a pretty way to say that.
Exactly.
Okay, just
That's LLM
sure.
as a judge. Now, there is there are still a few points on the floor that we want to get. And now it gets interesting because you might train a model to be a very good judge for this specific case. You might have a probabilistic way to validate some of the things, because we mentioned code, for example. Let's assume I have tests for this repository. Maybe just running the tests give me the result, or at least eliminates the problem, the problem solutions. So these are the ways that many different agents, not only what we do in Maestro, are trying to solve that gap of the problem of choosing the right answer when you increase test time compute. Yeah.
Okay. And maybe I want to make make it harder.
Yeah.
Maybe, or like say that we're talking about the test time compute in agents, but when I build something, when shouldn't I use this approach?
I don't think there is a way that you shouldn't use this approach, but I will say two other problems that I didn't mention, or one is a problem and one is just maybe this is not the most cost-effective thing to do. So there are a lot of simple things that just doing one call helps, because the model is already trained for that. And in a way, when you train a model, you go through the same process. It's the same process of increasing the probability of the model to answer correctly. It starts with some distribution, and you push it through reinforcement learning to get the right result on the higher probability. So in some of the cases, just one LLM call works, and doing all this scale out doesn't really bring value. If you have a system that knows to weigh it in, it just won't do it, right? And that's part of what we're trying to do with Maestro, is have something that knows the probability of things and knows what the expected cost and expected value, and then automatically increase compute, not brute forcing always with 16 rollouts, but doing it only when it matters. So that's one area where you won't need it. A second problem with this approach that I swept under the rug for a while now is you don't always get to parallelize without consequences. So let's say I want to run 16 agents and let them solve the same thing. And let's say that thing is, I want to have an agent sending you an email and trying to book with you the best time for this interview. In real life, I don't want you to get 16 emails at the same time, each with a different hour, and we'll try to solve. So how do we deal with agents performing actions that do state-changing things in the world, right? And not just reading files. It's very simple, to think about deep research agent, browsing the web, bringing 16 reports, and we choose the best report. But what happens when they change files? When they write to databases, where they send emails, and so on.
So it's the move from read-only agents to write agents.
Exactly. And write is with code, it's with real-life actions, it's with DBs, etc. And that's when it gets complicated, because one way is say, okay, let's do everything in a sequential way. We can maybe do rollbacks or some of the things we can ignore. Then it gets with a very high latency, which is not ideal. What we're trying to solve when we run multiple times is usually do it in parallel, so we don't have this latency cost. The other solution is try to have those sandboxes, and that's interesting, because in some cases sandboxing is easy. So for example, code, and again, this is something that already been done in other like dedicated coding agents. We have Git, right? So you can use Git work trees, you can use other methods, you can duplicate a repository, you can have a lot of methods of sandboxing what the agent is doing. But if we think about it, we can take this to other areas as well. So databases have transactions, so you might be able to do the same over there. And documents, let's say my Google Docs, it has version control. So maybe I can do things in parallel with suggesting, and at the end, after I chose the right trajectory, do rollbacks of everything else. So there are methods, but we need a systematic approach for this. So code agents did it for themselves, specifically for Git work trees. But what we believe is that we need to have a systematic way to do that in real world. So we suggest an extension for MCP protocol. So that can be supported on whatever. And then it's on the developer on the other side. They should have a method to create those sandboxes. And now any system that works with that can run as much agents as they want, and it will happen.
Essentially an extension for MCP protocol to work with agents that can write.
Right? Exactly. So that's on the interface level with the world. On the orchestration level, what we want to have and what we have inside Maestro is, so I'm going back for a second and tying things together. I mentioned earlier that one of the problems with existing approaches is the black box test-time compute. So I'm running full trajectory. But let's say I'm doing white box test-time compute scaling. And I know what every agent doing at every given time, and I have the ability to stop at certain points, to abort at certain points, to make them hold and wait, and so on. And if I have this ability, now I can create sort of sync barriers at decision points where something needs to change in the world. So let's take the email example of the two of us. Assuming I want to have 16 agents trying to book this interview. Maybe they have about 50 steps of looking at your calendar, looking at my calendar, asking me things that I don't care that will happen in parallel. I can parallelize this and then make a decision point that before they're sending you the email, I have to have a sync barrier. So instead of choosing at the end, I'm choosing in the middle point. And let's say that we agreed, we can open up again, and each of them can do whatever they need. So as long as we know how to identify the state-changing actions in the world, a white box orchestrator that can really look into what the models are doing, what the agents are doing, that can stop them, that can guide them, it can only stop or have those sync barriers at the right point in execution.
And this sounds, I think, very unique in the world. Can you maybe share a bit on how are we building this white box decision makers? Or
yeah, so I think maybe I'll walk through a few concepts of Maestro that are all built around test-time compute scaling. So we mentioned in the beginning that we don't want to brute force this scaling option, right? We don't want to have a developer writing some fixed code, always do 8 of everything or something like that. So it means that the core of Maestro at the beginning is to have a portfolio of things that the system can do, a portfolio of actions or agents. And that portfolio has to have two things. One, it's better to have a lot of different actions that help each other and build and span the solution space. So I don't want to just maybe take the top 10 strongest agents, but they all solve the same tasks. I want to have 10 that are more diverse and span the solution space. But the second important thing is I want to have some priors. I want to understand what is the expected cost and the expected value that each of these actions will give me on a new item, a contextualized new item. So when at inference I get a problem, I'm looking at my portfolio and I know that this, that, and that, these are the best agents to use and it will cost me probably $1. I don't know. And if I have more budget from the user, I can add more agents to the party. So that's the first layer. This again still speaks in like full trajectories of agents. In order to really open up and do this in a higher resolution, we added structured plans. what are structural plans? Instead of giving reasoning models, React agents, what most agents out there today are basically descendants of React agents. Instead of letting the LLM roam free, running their plans with text and things that you can't really control or parse as in a systematic way, we use structural plans. We have a planning definition language based on Python, and all the plans are created with that. It means that our orchestrator, Maestro, parse that, compiles that, and have full observability of everything that happens inside the agent.
And this is chain. How does this differ from something like small agents, for instance, that have coding plan?
Right. I think that's a very good comparison. We're not the only ones using structural plans, and this is part of the reason people are going to structural plans. But structural plans give a lot of value, for example, control flow and data flow, and that's what you also get with Python or other code methods in small agents, for example. But our differentiation or our approach was around test-time compute. So the kind of planning language that we built, it's a subset of Python, but it thinks of how you can later parallelize or how you can define what you want to have, so and not how to do it. And we separate those layers. So if you give a model free code to write your plan, you quickly get orchestration, logical plan, and the actual execution mixed up together. Because on the same line of code, you get the concept of, retrieving a document, but the actual call for the retrieval. But that doesn't let me scale that. So what I want to do is separate orchestration, say, I want to retrieve a document. I don't care how. And now the orchestrator can offload this to a lot of different tools, an agent that can do that. So that's the first difference.
Sounds like a successful PM who says to the dev team, right, this is what I want to be done,
exactly.
not how.
Not how, exactly. And the second thing is we want to keep it secure. Now, other methods of keeping it secure is sandboxing, and that's what some of the code for planning frameworks do. We just limited that language to things that model can't hurt. So they're only focused at orchestration. The idea is to focus that structured plan at what I want to do in terms of the logical steps. In a way, it's similar to things that users write to their agents in prompts, right? In free text, they say, first, try to find the best slot in the calendar, then contact Yuval, and finally put, it doesn't actually mention the calls, the API calls, the what write in the email, and so on. So we're trying to mimic that. So that's the second tier. So we said we have a portfolio of actions. Now we have a structural plan that lets us increase test-time compute not at the root level of the full trajectories, but at given points. Because maybe some things are harder and they require large expansion, and some things are easier. The last part that makes everything happen is the actual execution engine. One of the problems or pains in writing these kinds of agents is that you need to deal with a lot of manual work of parallelizing things, importing frameworks and thinking what race conditions between elements, and thinking of your specific workflow and optimizing it. Execution engine does that automatically in Maestro. So once you have that structural plan and you have those preferred actions, our engine parses that language, compiles it into a graph, and knows how to do all that magic automatically. So the developer doesn't have to deal with what's the race condition, how do I parallelize. It gives the budget, it tells you the plan in a high-level way, and the execution engine take care of the rest. So it can do eager execution of things that are maybe in a side branch and are independent. It can parallelize whenever it can. If you give it more compute, it will do more. So that really solves the pain point of actually building this instead of writing a lot of code to parallelize, to handle race conditions, to validate, to reduce. Maestro gives a system for that. And that's the last layer, I would say, in the core pillars of Maestro.
Okay, this was very interesting theory, explanation, structure. Let's talk about results.
Sure. So one example, we had fun with Sui Bench.
Everybody has fun with Sui Bench.
Too many are having fun with Sui Bench. It's a bit. Actually, it's a bit crowded and somewhat overfitted, I would say, at this point, because it's out there for a while, and new models and agents that are coming out they are aware of this data set. There's some nice academic work that shows that. But anyway, it's a good playground, at least for us to validate what we did. And a few interesting things that we saw. So first of all, the potential. In terms of potential, I mentioned a lot about running multiple times gets you to a better score. It's true. We ran multiple times, a lot of models, and indeed their accuracy goes up if you run it 1, 2, 4, 8. And now I'm assuming I have a perfect validator that knows to choose the right answer. The more interesting part is it's not only that you get better results, it's also cost effective, because one of the things we saw is that running GPT-5 Mini, for example, 4 times gets you to a better score at lower cost than running the large GPT-5 once. So that's a classic case of what I mentioned about test-time compute scaling and knowing the probability and the cost. So the system should say, oh, it's better for me to run the cheaper model 4 times for solving this item specifically.
So it's funny, actually got spend more, maybe, like more runs. It's kind of like not intuitive.
Right, and it's cheaper because these 4 runs are cheaper because the ratio in the price between the 2 models are not by 4. And it's faster because if you have Maestro to parallelize this, it's also faster because you did it in the latency of 1 run of GPT-5 Mini. So it's faster, cheaper, better. Like everything, right? Reach
shut up and take my money right now.
Exactly. So that's one thing that we saw, and that gave us a boost on the confidence of this approach. But this is something that others have shown in the past. Example, Tray Agent and others showed this potential. The real power here is to do that automatically. A second interesting thing that we saw is the structured plans that I mentioned earlier. So we have our structured plans, and they give us power to do test-time compute. That's the main goal, but they give other benefits as well that we mentioned, or that others are looking into structured plans as well because of the same things. It gives you control flow and data flow. It enforces the plan that the model is trying to do, because sometimes model want to do something as an agent, but then they get stuck in a loop or missing the point. So it gives a structure, and we saw that this alone, our structural plans, whether it's letting a user write a general purpose plan or just having a planner model create plans dynamically, in both cases, that also improves results by 3, 4, 5 points per model. So that's really interesting and nice to see. The last thing is, and I'm going back to the first layer that I mentioned, the action portfolio. The last thing was to see, so let's assume we have that perfect orchestrator that knows what's the best thing to use for every item. What will it do? And we looked at it on Sweetbench. We have a lot of different trajectories, varying models in size, quality, and so on. In a way, that's the action portfolio that I mentioned, because while some of them solve the same things, some of them not. Like some of the items are solved by one or not solved by others, or they can be solved with a cheaper model, so you don't need to go to the big one. So we ran this like theoretical test, and we see an amazing potential boost of what you can get for the same dollar. So let's say, what is the score I can get in an average of 25 cents per item? And you can see that that optimal curve is way better than any of the other trajectories of every model out there. And that's what an ideal portfolio and an ideal orchestrator would do on a benchmark like that.
So there's like a really big gap that still needs to be filled.
Exactly, and that's what we're doing with Maestro. Closing that gap by having this portfolio and a smart way, an automatic way to choose the right thing, to scale only when you need it. That's the idea behind the framework.
Well, Or, thank you so much for being here. I learned a lot about what we're doing here in the company.
That's a problem. We need to talk about it.
Yeah, but that's the way I do it. I just bring C-levels here to the podcast and I learn. And everybody, stay tuned for other episodes of YAAP.
Thank you.
I get you to do that.